So, hello everyone. I'm going to present this thing to you to hopefully help you solve all your problems with deadlocks. Problem. Well, deadlocks are the problem. I guess I just have to introduce what a deadlock is. In our work, we focus specifically on generic servers. Who knows what a generic server is in Erlang? It's like a two-stage pattern in which you essentially spawn a process in which you can make blocking calls. You can send a message, and the service picks it up, keeps working on it while it's not doing anything else, so it's doing it completely sequentially, and then it replies to you with a response, and it just handles one such request at a time. Okay. So it's easy to imagine that such systems based on generic servers can run into deadlocks. You can have cycles, and they happen in production. We have evidence from the industry that this is actually a problem. Unfortunately, Erlang provides only with trivial deadlock detection. So if a generic server calls itself, then you get a deadlock notification, of course, because it can detect it. But if a deadlock consists of more processes, which is usually more concerning case, you get no feedback about bad stuff happening other than a timeout simply. So it's hard to distinguish low performance from a deadlock, and also it's hard to get any decent feedback of what processes have been deadlocked. So for this, we introduced DDMon, which is implementation and artifact to our other talk we do at OOPSLA, correct black box monitors for distributed deadlock detection. That's the theory. So if you want, we have formalized everything I'm going to say here, and in this talk, I'm going to just describe the implementation. So DDMon is a replacement for generic server, which acts as a wrapper over the actual generic server process. And the aim is to have minimal code intervention, so that if you have a system, you can just easily apply it and have deadlock detection almost for effortlessly. So how you apply it? If your project is written in Erlang, you just replace all the references to generic servers with our DDMon module. You can do it manually. You can also use parse transform if you'd like, and then with some basic interfaces should work. In Elixir, you can use alias, which makes things even easier. And if you do it, you just get deadlock notifications whenever they happen. So how does it work? First of all, how DDMon actually interact with generic servers. So for each generic server in the system, another process is being spawned, a monitor. This is exactly what it looks like, which just oversees communication of one particular generic server. So each generic server receives one monitor. And to make it clear, I don't mean like Erlang monitor, which receives notifications only if the process dies. Like a monitor more comes from the theory of it, and just think about it as a separate process. It's in this model, its job is to intercept all messages and act as a proxy between this generic server and the system. So it receives a message, sees what it is, and then passes it down to the actual server, and the same happens for outgoing messages. In the meantime, this monitor can communicate with special messages called probes with other monitors to establish some knowledge about the global state. So how do we detect deadlocks? Well, it's not rocket science. We just look for cycles, and so say we have a system based on 3 generic servers. Each one receives a monitor. There comes a call to the first one, which is then passed to another one, S2, and reacts to it by calling S3, and S3 calls back S1, and we have a deadlock situation. So in this case, if the monitor observes that it received a request while waiting for a response, it will send this probe message to whoever called it, like against the wait for graph, right? This message gets then propagated, and if it returns before a response is received, that means a deadlock has emerged. As simple as that. And this algorithm we have proven correct. We have done it in Coq, so there's no discussion about it. This whole thing is a model, so if you'd like to see how more details about it, you can just read our OOPSLA paper or attend the presentation later. I'm going to talk more about testing it. So just to see how it looks in practice, we created some example system to evaluate the artifact in which we produce microchips. So we have producer processes which produce microchips, whatever data it is, and they call another kind of generic service called inspectors, say, who validate their produce and return OK if it is found. However, inspectors might also call other producers for some reference method data. That's just the story we made up. So if we take as an example a system with 2 producers and 2 inspectors, one can make a call to producer 0, which will then ask inspector 0 to validate its result, and I0 might ask P1 for its metadata reference. And they can receive responses to their calls, and a similar thing can happen in parallel. If, however, in the same scenario, these 2 things would happen in parallel, it's easy to see that they can call themselves, causing this cycle here, and they would not recover. So just to show how it looks in practice, visible. We have this implemented. The code is on GitHub, so if you'd like to see how it works, that's there. Yeah. You can just find out, put the link later on. Get this clear, so we can run this system, and we see that we non-deterministically get deadlocks. For example, here, the first call to the system yielded a success. This time we got a timeout because a deadlock has emerged, which you can see from the log. However, if we do this completely unsuspicious send command, which uncomments these 2 aliases, that's the only thing it does, we employ our monitoring. So we replace references to generic server with our system. Then we also need to turn on monitoring. Okay, nothing. No deadlock happened. Yeah, we got an immediate deadlock description. So we can see that the cycle has been detected and the system terminated early without timeout, and we also get the list of processes. So that's how it works. How else we tested it? Well, we performed many auto-generated tests. We created a DSL in Erlang, which allows us to describe specific scenarios of processes communicating with each other and possibly running into clashes. So here we can see this example implemented as in our DSL. So for example, here we have 2 sessions. I0 begins with some initiated process number 0. Then there's a call performed to process number 1, which then calls process number 2. And then they would just receive replies in the opposite order. Meanwhile, I1 does exactly the same thing, just with different processes, except that it waits for random time before that. So using this neat system, we can quite precisely replicate scenarios which appear in real systems and see how the DDMon behaves. So we've performed many tests for correctness and also for just to see the performance of the system, like what's the overhead of having it here. So obviously, if you just count blunt messages, the overhead is like 3 times increase in messages sent, because in order to a single communication turns into 3 messages, that is forwarding outward, outside, actual communication and forwarding inside. But in practice, we believe that this forwarding is going to be quite a quick operation, because there's no I/O involved if both monitor and the generic server run on the same node. It's just a memory operation. A trick you can do to minimize the number of probes emitted, however, because that's significant if you take a look at this red line, for example, maybe I should say what these numbers mean. the vertical axis says how many messages have been of different types have been exchanged, and horizontal is just time that passed in a quite large randomly generated system. So here, for example, in this chart, we see how many queries and probes and responses have been sent around. The number of probes is quite high. But on this chart on the right side, we implemented some tiny optimization in which we just delay deadlock detection by 5 seconds. So like whenever, instead of initiating this search immediately, we just wait for 5 seconds. If we haven't received a response, we just do this circle detection. And that completely obliterated the use of probes. There's just the overhead of messages just disappeared. So the conclusion is that the overhead is quite small. So just to summarize, DDMon provides generic server-based system with deadlock detection. It's quite easy to apply, and its correctness has been proven formally in COC. It's not a production-ready implementation, of course. It's merely a prototype, but like it proves the point. And that's it. Thank you for attention. Positive views. GitHub.
Right. So a question. So when it detects a deadlock, it will show which were the processes involved, but not the actual calls or
no, but it's relatively easy. Like depending, like since monitors intercept messages, they can see what messages like cause the deadlock as well. So it's just a matter of adding logging. The problem is like if you send a lot of data, then you have to store it somehow, for example, and that might be inefficient depending on how you would like to save this information.
Yeah, maybe have some kind of tag of the messages, which is failing.
Yeah, this is a possible extension, but sure. Yeah. Also, maybe what I should have said, which I didn't, is that it neatly allows to distinguish the processes which participate in the cycle from processes which are dependent on the cycle because they call some deadlock process. Because technically those also are going to await infinity, but they are not the source of the issue. The source of valuable information in debugging.
One more question. So you said that the optimization is delayed when you start doing the cycle check, just to see that something seems stuck, if I understood correctly.
Yeah, so like if we go back to this animation, so when a call happens to it when a call is received by a monitor whose generic server is locked, but because it's waiting for a reply, it can just, instead of sending this probe immediately, it can just wait for some time. That's easy to configure and it has huge impact on.
And the time is proportional or is dependent on the timeout of the call, or it's
it should be like adjusted to the size of this cycle and like the sum of all those calls. Because the cycle is big, then I guess you can receive a reply after a long time.
Like on everything time out before you start.
Okay, so in this situation, we assume no timeouts. Okay. So because if you have a timeout, then you technically, like theoretically, don't get deadlocked because you don't actually need to receive a reply in order to proceed. That's the philosophy here. Because if you apply timeouts, then actually there's another way, and deadlocks are supposed to be permanent.
Still an error to usually have a timeout and abort, like sometimes you have the timeout on the call and just fail, and in the log you will have got something timed out and you still don't know why it happens.
Well, if you have timeouts, then yeah, you will not get good deadlock detection. That's like if with this you should not use timeouts to handle deadlocks. Essentially.
Can I to clarify? So, indeed, as Radek said, you should configure delay so that the probe is sent maybe before your timeouts expire. Otherwise, you may get basically incorrect deadlock notifications. And at the moment, basically, we've proven that every deadlock report is precise. So if there's a deadlock is reported, if a deadlock is reported, it is real. But if you put timeouts in the mix, then you may get notified about a deadlock that was resolved by a timeout before. Maybe it's still good, depending on your application, but it is something you have decided not to do.
Well, Wednesday. Ah, okay. But also, I think the bigger problem is actually that monitors don't really know what the timeout is. Like this information is not propagated forward; it stays in the generic service, so the monitor kind of know when to abandon the call. Yeah.
Yes, just to understand your point. So as far as I understand, having a cycle among actors is not the only condition for the deadline. So to have a deadline, if I remember what I learned from operating system courses, there were 4 conditions for the deadline, and one of them is having a cycle. So probably your algorithm, so you do not explain all the detail of the algorithm. Perhaps there are more than checking the cycle. That is my understanding.
So with this, like, assuming we are talking about generic servers which do not do timeouts, we model that in hoc, and we have a proof that being deadlocked is equivalent to having a dependency cycle in the network.
Having a cycle.
Yeah, because like, the definition you're referring to likely is first of all more global, so it requires that the whole system is actually stuck. Here we are talking just about local deadlocks, where just a part of the system can get blocked. And as far as I remember, the definition, I've been taught they were usually referring to common resources, and here we are talking about message passing. Like you can model them as resources, but it's slightly different setup. Yeah, be good. And thank you for your attention.